Now on beams, when you load up a beam, such that if you put a couple of bricks down, put a board across it, stand on the center of it, it would bend. It might even break. If it breaks, that means the tension at the bottom of the beam, or if the beam was like this, the tension at the bottom was too great for the tensile load of the material, and it breaks. On the top, it's in compression, and it wants to crush itself. So if you have a piece of wood sitting on the bricks, you step on it, the bottom tears apart in tension, the top pushes against itself, but wood's pretty good in compression, and it probably would show no signs of compressive failure. Concrete is very good in compression, lousy in tension. If we have a beam and we support it at the ends and we load it up here, this is the tension force I mentioned. High tension. This is a compressive force. So when you load it up, this wants to pull apart, this wants to go together. What's interesting, if you measure the tension in this beam, inside it would be a little less tension, and by the time you get to the middle, there's no compression or tension. And the same thing goes for the compressive forces. So the tension and compression reduce to the point where it's zero at the center. So now knowing this, the engineers years ago decided, if that's the case, let's put all of the strong material at this end, at this side of the beam, to withstand the high tensile forces. Let's put a gutsy part of the beam here to withstand the compressive forces, and then we just need a web to connect the two. So what they did, they took a piece of steel there, piece of steel on the bottom with a lot of guts to it, and then connected it with a web that all it had to do was keep the two pieces together, and they discovered the I-beam. So now all your bridges are built with I-beams. Any structural thing is built with an I-beam. All of the compressive loads are here, all of the tension loads are here, and this thing just goes along for the ride.